what they've been doing to make all of this possible. So over to you, Mitsuhisa.
Okay. Oh. So can you hear me?
Yes, that works well. Okay.
So let me start. So my name is Mitsuhisa Sato from the RIKEN, the RCCS. I'm Deputy Director of the Center for Computational Science. That is the host organization of the supercomputer Fugaku, a new one. So, and I've been the Deputy Project Leader of the flagship 2020 project. That is the project to develop our flagship machine following the K computer. And in that project that I'm leading the architecture side, I'm managing the architecture development. So, this slide is summarized our project, and the mission is developing the supercomputer flagship machine. And at the same time, we have been developing the wide range of application, which is expected planning on in a Fugaku machine. So as you know, I'm going to talk later more detail about our architectures, but the many core architectures which is connected by the TOF network, the sixth dimensional, that is the dedicated network for the Fugaku machine. So, and the status is that something like this. And the last August, the K computer, our K computer is decommissioned and stopped services and shut down. And we removed all the K computer from the machine room, and we now installed a new machine in the same room. And after decommission the K computer, we got access to the test chip. And okay, pointers. And at the moment of the last supercomputing conference, the Fujitsu announced the commercial version of our Fugaku machine, that is the FX1000. And also at the same time, they announced a cluster version of the same chip and A64FX. That is the FX700. So, and we are very excited about the collaboration, Fujitsu collaboration with the Cray. And you can buy our machine from the Cray. That is very exciting things. And at the moment of the last the supercomputing conference, we got a final test chip, and we finally fixed the clock frequency 2.0, and it can be boosted to the 2.2. And using the small two-cabinet two-rack machine, we got the Green 500 last year, and this year, as you know, we got the first position of top 500, and the HPCZ and Graph, and new benchmark of the HPL AI. So we are very happy with that. And status is that delivery is started from the December of the next year, and completed is the May. And that means that we have all cabinet, and cabinet number of cabinet is 432 rack. And so currently we are the testing and adjusting, and part of the system is also the hosting some computation, and not just only the testing. So this is the schedule, the timeline of the project. project is started from 2014, and we are now in the 6 years. We got a machine, and we are going to start the public services from the Q1 or Q2 of the next year. So, okay. And this is the kind of certificate of the GRI 500, the last supercomputing conference. The biggest things is that this chips can achieve the same level of the power efficiency of the GPU. So that is the almost 17 kiloflops per watt. So at the time of the ISC this year, so new Intel machine, new the NVIDIA machine is the A100, and also Japanese the special purpose machine for deep learning is one Green 500 at the moment of the ISC. So okay, so this is the picture of the machine room. So this used to be, there used to be in a K computer, this room, but we removed the all cabinet and installed a new one like this. And very clean and the implementation. So, and this is the detail of the top 500 and HPCZ and HPDAI and graph. So one thing I'd like to put the emphasis is that as a result, at the time of the ISC, the machine is almost 2 to 4 times faster than every benchmark. So this is the very exciting thing. So, and okay. So, and as I said, the machine is already used for the DL application. So, and especially the part of the machine is already dedicated to the application which is the fight against the COVID-19. So there is the 5 projects now, and 3 is the medical and pharmaceutical application, and another is that more sociological and pandemic simulation. So this is the a kind of docking simulation for finding the new candidate medicine for COVID-19, and 2 things to these application is MD simulation to figure out and structure of the COVID-19, the virus. And let me, so this is the very interesting simulation. I'd like to show the result. So this simulation is the CFD simulation to figure out the drop rate, the trajectory. So that means that within the train cabin, as you know, in Japan, the train used to be very crowded. So how the air flow and the drop rate is fly within the train cabin. So interesting finding of this simulation was that if you open the little bit window of the cabin, then the circulation of the air getting the very good compared to the in closed the air conditioning. So, and another example is that so this is the simulation. Oh, it doesn't move. So this is the simulation of the office. How fly the droplet is within the room, office room, and how to avoid drop the virus in a droplet. So okay, so let's move to our project. So we set 3 KPI on a Fugaku at the beginning of our project. One is the power consumption, extreme power efficient. So our the facility capacity, the power capacity is that 30 to the 40 megawatt. So the first the KPI is that to get the highest the performance as possible as that we can within this 30 to the 40 megawatt. The next one is that an effective performance of the real application. So we don't care getting the top one of the benchmark is not our priorities. So the important things is that the performance of target application. So at the beginning, we expect 100 times faster than a K computer in some application. So now we figure out an MD application called the Genesis, and also the Nikon LATKF. This is a climate and the data simulation application. We share to get more than 100 times faster than these applications. The last one is that easy of use. So because of this system is used to the wide range of application is all over Japan and all over the world. So ease of use, the feature is very useful. So this is the one of the key item for co-design with the application developer. So finally, we decide we are not using any GPU. So we don't have no GPU in the system. So that means that shared memory, the programming can be just a programmer can use this system using the OpenMP and MPI. Okay, so this is the target application, and this is the expected speed up over the K computer. As you know, as you can see, this Genesis and also LATKF, that this is a climate simulation. We sure that we can get 100 times faster than a K computer. Another application is 30 to the 50 times faster. So okay, and this is okay. Oh, so and this is the architecture of the our CPU chip A64FX. So the instruction is set is the ARM V8 and plus the scalable vector extension. This is the SIMD vector features. So length of the SIMD is 512 bit, and we have a 2 pipe of this SIMD. And the number of cores is 48, and plus 2 or 4 dedicated the core to running the operating system daemon. And that means that the user can use the 48 cores in the chip. So this chip, the 48 is divided in 4 NUMA nodes like this, and each NUMA domain, NUMA node we call the the core memory group, CMG. So each CMG contains the 12 core. So in these core sharing the L2 cache and also in the memory. The memory is the HBM2. That is the on-package stacked memory. So each the memory is the 8 gigabyte. That means that with totally the one node has the 32 gigabyte. And the silicon technology is the 7 nanometer FinFET by the TSMC. So thanks to this advanced silicon technologies, and also very good engineering, we can get a power efficiency of 15 the gigaflops per watt for the DGM. And common programming model, that means that at the co-design phase, we decided to support this programming model, MPI process, MPI and OpenMP hybrid programming. In this programming, the MPI process is running on one SIMG and communicate to the another node and another the CMG by the MPI. But this network on chip is also supporting the coherence, memory coherence. That means that these memory can be shared by these cores. That means that 48 threads, the OpenMP is also supported. Okay, and this is the chip photo. So, and okay, this is the cores, and this is the L2 cache, and this is the TOF interface and the PCI interface. And it is mounted on like this, and on a silicon interposer, the HBM2 is mounted like this. So, okay. And, okay, and we have this is same the information. The clock frequency is 2.0 and the boost is 2.2. Okay, and network is also the TOF network. This is the same topology of the K computer. This is the important for a kind of compatibilities for the large scale parallel application. So, and the TOF interface is also integrated on the same chip. And we have the 6 DMA engine called TOF network interconnect. Okay, speed up. And the processor and optical interconnect is water cooled like this, and one board is on one board, 2 chips is mounted like this, and installed in a cabinet like this. And one rack is contained 384 CPUs. This is a very dense the installation. And okay, and this is the storage system. So we have the 3 level the hierarchy storage system. First layer is the SSD, and one of the 16 computer node that have the SSD. This node is called IO node, and this SSD is used for the cache for global file system, and also temporal file system for local file system. And the local file system is the global file system is the raster-based Fujitsu raster-based global file system. And also we are thinking and third layer the cloud storage. And this is the comparison to the K computer and the Fugaku. And I'm going, and I don't say not much data, but in this the number is the single precision. So using the single precision, the peak speed is going to be exascale. Yeah, so we are happy with that. Okay. Okay, and let me show about an benchmark result in UK benchmark. and Cloverleaf and TLeaf. Maybe you already know about this benchmark, and we compare our system with the SunDX2 and Xeon processor and dual the socket. So, and this is the Cloverleaf result in one node, one chip. So without MPI. So you can see this is the execution time, and this is the relative performance of the one thread here. So as you can see, our chip is very comparable to the dual circuit of the Intel Broadware. So, and good scalability within the chip in this kind of application. And TLeaf is a evaluation of MPI program within a node. That means that the one MPI process is running on the CMG. We change the thread in each MPI process. Again, this is the execution time, and this is the relative performance of to the one thread of the A64 Apex. So, and this result is very good. And compared to the Xeon and SunDX2, our chip is almost double of the performance for this benchmark. So I think this is because of the good memory bandwidth and vectorization. So, but the Rulish, you know, this is the US benchmark. So, and evaluation using the one CMG without MPI. So, and compared to the SunDX2 and Broadware, our chip is not so good because we found that low vectorization. So that means that if the application cannot be vectorized so well, then the performance is not so good. So, okay, let's move to the software stack. So, and this is the software stack, and basically the Linux, Red Hat Linux is running as a node operating system, and also the MPI and programming language. And I'd like to note that we are working on a SPAC, the packaging, and the user can using the install the application using the SPAC. Okay, and this is the system software and programming model for current Fugaku. As I said, standard programming model is the OpenMP and MPI. And for the MPI, OpenMPI by the Fujitsu, and the Impeach is supported by the Riken. And the Fujitsu is going to support the OpenMP version 4. And also, the low-level communication layers API is provided to make use of the TOFD interconnect and directory. And also, and the container and the virtual machine is available, KVM singularities. And DL for Fugaku is the AI library. And this library is already used for Chainer and PyTorch and TensorFlow. So using this library, I would say that the performance of the one chip is comparable to the half of the GPU, and the test but we have many nodes. So it is good performance if you are using the many nodes for the training. So, and many the open source software will be ported by using a Spark, as I said. And the system software and programming tool, the master library is developed by the Riken. The MC kernel is the lightweight kernel. This is the very useful the kernel the mechanisms to jitterless environment for the large scale execution. And Excalibur MP is the direct-based Pegasus language, which is our team is developing. And FDPS is the framework for developing the particle simulation. And also, the mass library team is developing the eigenXR. This is the eigenvalue mass library for the large-scale system. So XKMP is the Pegasus language and the direct-based extension. And this support and global view and query. And I would say, I don't say not so much about this, but spec of Excalibur MP is now converged. So we are moving to the next version, the Excalibur 2.0 for task parallel programming. So, but the Excalibur MP is now available on the Fugaku. If you want to use the Pegasus language and query, you can use this language. And performance is was very good compared to the K computer. And also, this is the framework of particle simulation. So user just define the particle and also definition of the interaction. This framework is supporting the domain decomposition and the particle exchange and the particle interaction. So, and this framework is also working for the GPU. So they got a very good result, and gravitational the n-body scaling is like this. It's scaled up to the all node of the K computer. And I think at this moment, challenge for the Fugaku is the two things. One is the task-based programming. So I think to exploit the parallelisms, the simile and the many cores. So we need a much parallelisms. So, and we want to overlapping the computation and communication. So I think I believe the task-based parallel programming is very useful for also Fugaku. And currently, some people is looking at the OpenMP 4.0 task and the MPI. That is supported by the OMPSS also. But we are now designing to in a task-based programming in a global address space language. And another thing is that how to exploit the simile. So simile is the key for performance of the A64X. So one of the solution is that the OpenMP simile directive. But of course, Fujitsu compiler is doing a good job by the compiler optimization. So especially the software pipelining is very effective to get a performance in A64X. So, and my team is working for the OpenCL for SVE using SIMD SVE. So, and beyond the Fugaku, I have no idea about that, but the system is going to be the very heterogeneous, accelerator-based heterogeneous system. So I think our team is working for the Excalibur MP plus integrated on OpenCC to programming the accelerators. And also task-based offloading for the accelerator is the one of the research issues for this kind of the future system. Okay, time is up, and this is okay. And concluding remarks. And okay, we have the 3 KPI, and we found that our system is very well-balanced the system several application thanks to the co-design. And currently, we already have the early users, including the COVID-19 application team. So finally, my message is that so our system is fortunately or unfortunately very homogeneous system. That is very different from the US approach. So and that is a kind of result of the co-design. But I would say that the kind of dark side. So dark side means that by co-design we are doing, there is no destructive architectures, but are easy of use. So people can, our system using just the OpenMP and MPI. But I think for the next system and the future system, application-specific accelerators is needed for the more power efficiency. Or my question is that, or is there any room for improve the existing process architectures without the accelerator? So I think accelerator could be is embedded to the processor or the ALU. In that case, I think the current GPU programming is cannot be used anymore or something like that. So thank you for your attention. I'm running a little bit longer. Thank you.
Thank you, Mitsuhisa. Thank you for that very illuminating talk. We're almost out of time, but we had 2 questions that have come in on the Q&A during the talk. If we can try and just quickly answer those. The first one from Thomas Hayward Schneider was a question about the timeline. And he noticed that there was, in the original timeline, quite a big gap between the system being installed and then it being available for kind of public science. And what's happening in the meantime, or might the public science be brought forwards now?
That is a secret. No, of course, the small system, the medium scale system and that is for example, for the quarter of the system, 1/4 of the system is working. But if we extend the MPI to use the whole the nodes, then we got the scalability problem. So, and currently we are going to solve that kind of the problem. So I would say that medium scale, that is the 100 rack is running, but 400 rack is not running yet.
I see. So it's the system still being sort of shaken down and there's tuning and things like that.
Yeah. That's right.
Right.
Yeah.
Okay, good. Thank you. Second question was really a question about how is the A64FX so energy efficient? What's the secret?
I think a major the contribution is that silicon technologies, that is the 7 nanometer FinFET, and also the FEED2 the microarchitecture design, which is doing the power gating or something like that. And also, I think HBM2 is also power efficient compared to the ordinary DIMM, DDR memory, I think.
Great, thank you. There's one more question coming in, but just so we don't go too far off schedule, perhaps you could answer that one by text in the chat after we moved on to the next speaker.
Okay.
So, thank you very much again, Mitsuhisa. That was really illuminating, very exciting to see what's happening with Fugaku. Thank you very much.